So in this, we'll see some of the problems and normals of the parabola. We have already derived the result that from any point outside the parabola, namely h comma k, we can draw three normals, and the relations among the feet of the normals t1, t2, t3 are also obtained. And if we have 2 points t1, t2 on the parabola, the point of intersection of the normals at P and Q, they are also derived already. So these problems what we are going to discuss here will be based on the result which we have obtained already. So in the first one, we will see only the outline of the problem, not the entire working rule of the problem that we are going to have. First we'll have a few examples and then solve problems. And also the exercise problems which are solved. So if chord PQ of a parabola is fixed in direction, show that the normals at P and Q intersect at a point on a normal to the parabola. So what do we mean by the statement? If a chord PQ of a parabola is fixed in direction. So let us consider a parabola, and we shall consider 2 points, say P and Q. So here we have P with coordinates 81 square to 81, which we simply denote as T1, and another point Q, both of them are on the parabola, with coordinates 82 square to 82, which we simply denote as T2. And this chord PQ is in fixed direction, which means we know the equation of the chord PQ is given by this. So with this fixed in direction means its slope. See, all this we know already, that the slope of this line is 2 by t1 plus t2. So this is constant. So that is the meaning of saying that the chord PQ is fixed in direction. Then with that, what we have to show is that the normals at P and Q intersect at a point on a normal to the parabola. So this is what we are going to prove. So what is the method involved? Let the points P and Q be T1 and T2 respectively. Let them intersect at the point x1, y1. So what we are trying to prove is this x1, y1 lies on a normal. That is, this equation, this point satisfies the equation of a normal at a point on the parabola. So that is our intention. So the equation of the line PQ known to us already, its slope is written, and that is given to be constant, so that is taken as k. So from this T1 plus T2 is equal to 2 by k. Now we know that from any point three normals can be drawn. So we have T3 to be the foot of the third normal drawn from x1, y1. We have already talked about T1 and T2. So we haven't talked about T3. So for that reason this is given. And this is known to as T1, T2, T3 are the roots of the equation, because if the normal passes through x1, y1, we are replacing x and y by x1, y1, and the relation among the roots and the coefficients also known to as. So T1 plus T2 plus T3 is 0 because there is no t square term, and already we know that T1 plus T2 is 2 by k. So using this we get T3 to be minus 2 by k. Now T3 satisfies this equation actually. So it's a root of this, so it has to satisfy. So we are replacing our T3 by minus 2 by k. So and substituting that in this equation we get this. So this is to be simplified after simplification, because we want to say that this x1, y1 lies on a normal. So for that we are dropping the suffix of x1, y1, even though here locus is not asked. X1, y1 is a point on this equation, on this line rather. So here substituting t for minus 2 by k, we get the equation to be like this. Why it is converted as this is it's a parameter and this is also a parameter, so that now we can see that this is the equation of normal to the parabola at the point t, at the point t. But if I consider t, then it is 80 square to 80. So if in the place of small t we have capital T. So again we have and these two normals intersect at a point on the normal to the parabola. So that is established. So main point is that it's in fixed direction. So that leads us to all these um, equations. Now prove that the circle passing through the feet of the three normals to a parabola drawn from any point in the plane passes through the vertex of the parabola. So this question can be asked in section A. So for which we'll have to just quote that from any point three normals can be drawn and the sum of the roots is 0, and this also we have derived. Circle and the parabola intersect in 4 points and the sum of the 4 roots is 0. So we use both, and this is known to us from here. And using that here we get this. So this is one of the points of intersection of the circle with the parabola, and therefore that we are getting a 0, and that in turn implies that the circle passes through the vertex. So in this just the idea alone that we are going to have, not the each and every step of the problem. In this we are given three normals from a point to the parabola. Cut the axis in points whose distances from the vertex are in arithmetical progression. So that is the condition given to us. Then with that we are supposed to prove that the point lies on the curve. So it is three normals are drawn from a point. The locus of that point is only we are trying to prove as this curve, right? So this is what is given from any point x1, y1, or rather you consider three normals at the points t1, t2, t3. Let them meet at the point say x1, y1. The locus of this is to be found out. So if we need to find the locus, then condition must be given, only then locus can be found out. So the condition is when these normals cross the x-axis, whose equation is y is equal to 0, when these normals cross, suppose we name them as A, L, M, N, then we have naturally the coordinates to be, because when you replace y by 0 in the equation of the normal, then cancelling one t, you will arrive at 2a plus 80 square. So you have t1, t2, t3, and therefore 2a plus 81 square 0, and m will be 2a plus 82 square 0, and because all of them are points on the x-axis, these are 0. And the coordinates of n is given by 2a plus 83 square 0. So now what is given is these these are in AP. So these are in AP. So we have two. These are in AP. So we know that three points alpha, beta, gamma are in AP when the difference between the first two is equal to the difference between the next two. This can be rewritten as 2 beta is equal to alpha plus gamma. This is a result or definition from theory of equations. So theory of equations tells this condition, and we are going to make use of that. So we have suppose I name this as alpha, and this is beta, and this is gamma. Then we have 2 times beta, this is beta, so 2 times beta is equal to alpha plus gamma. So that is the condition used. So in order to find the locus, we need to have a condition. So this is the condition given. So this simplification gives one such relation. Now t1, t2, t3 are the roots of the equation, already what we have considered, this one. So in that you are dividing throughout by a, so that you have this, then the relation between, even without dividing also you can do it. So you have these three relations which are known relations to us, and we have to eliminate T1, T2, T3 from 1, 2, 3, 4. So that part is discussed here. So then you will arrive at, by dropping the suffix, you will get the locus. So the condition, whenever locus is asked, what is the condition given, we have to have an eye on that. So those problems are example problems, and this is given in your textbook, uh, exercise 32. So it's not that from this that you are going to read out the problems. We will have them one by one. So the first one, find the feet of the three normals to y square is equal to 4x from the point 6a, 0. So the equation of the normal at t on y square is equal to 4ax is given by this. And we have given that this passes through the point 6a, 0. So replacing x and y by 6a and 0 respectively, this is what we get. Solving for t, you get 3, because it's a cubic equation. 3 roots that you have, 0, 2 and minus 2. So correspondingly you will have the feet of the normals to be 0, 0 corresponding to this, and then 80 square. So t square is 4, so 4a, 4a, and then the same way 4a and minus 4a. So 80 square to 80 is the general form of any point on the parabola, which is simply denoted as t. T stands for 80 square to 80. T on the parabola stands for 80 square to 80. So you are replacing this, so you get this. So here, instead of this a, suppose I am given 8x, say, which means your a is 2. So instead of 6a, 0, you are given, say, 12, 0. Then in that case also you must know how to do the problem. So this is the general case, and in particular for various values also the technique is to be learned. This can be asked in section B, sometimes in section C this can be asked. So if x1, y1, x2, y2, x3, y3 be the 3 points on the parabola y square is equal to 4ax, the normals at which meet in a point, then we have to prove something. Again, usual procedure, equation of the normal at t you write and let it pass through hk, then you have this equation, and the relation among the roots t1, t2, t3 and the coefficients, too many times that we have come across this, and for convenience sake we denote I, xi, yi, instead of writing x1, y1, x2, y2 like that, we are writing just xi, yi, I taking the values 1, 2, 3, and here instead of 81 square to 81, 82 square to 82, 83 square to 83, we simply denote 80i square to 80i. So my xi stands for 80i square, y stands for 280i, I range from 1, 2 and 3. So what we need to prove is this. So this relation LHS you consider, and just substitute these values and simplify, you will get this. So when you simplify this, you have to use the fact that t1 plus t2 plus t3 is equal to 0. So t1 plus t2 will become minus t3. And the same way here minus t1, here it is minus t2. And then cancelling the terms, that you will get 0 on the right side. And this is just purely using the distance formula, you can arrive at this. But what is given to you is the normals at PQR on this meet at O. It is not origin, it is some point O, and that is taken as HK. In the context, O stands for, you would have denoted somewhere your O as the origin, but in this context your O stands for the point with coordinates H, K. Then focus is known as just your distance formula is used, and the relation summation t1 0, summation t1 t2 is 2a minus h by a, all this relation among the roots of the equation, normal equation, and the coefficients. So that we are using, and PQR are taken as 81 square to 81 and so on. So SP square you find, SQ square from which SP you can find, SQ you can find, SR you can find. Now in the LHS you have to consider SP, SQ, SR, so that is written, and then that has to be multiplied. And here again from theory of equations, the relation summation alpha square is summation alpha the whole square, summation alpha the whole square minus twice summation alpha beta. So that formula is used here, and similarly you have summation alpha square beta square formula, and that is used for the second one. So theory of equations result is used here, and then these values are known. Summation T1 stands for what, summation T1 T2 is what, T1 T2 T3 is what, they are known. So just substitute, simplify, you will get LHS to be equal to RHS. And then the next one, the normals at PQR meet in the point HK, prove that the centroid. So all these problems, if you notice, you to some extent you will be using the relation among the roots and coefficients in the equation of normal. And then later part of the problems involve the point of intersection of the normals at T1 and T2. So when it comes, we will see that. So here again the relation, you are right, you know the equation of the normal and the relation among the roots and coefficients, and centroid is given by, I know the vertices of a triangle, then from which I have got the vertices. So here the vertices are given by 81 square to 81, 82 square to 82, 83 square to 83. So if it is x1, y1, x2, y2, x3, y3, then x1 plus x2 plus x3 by 3, y1 plus y2 plus y3 by 3, y coordinate. So that gives the centroid of the triangle PQR. So using that known result, that is how do we find the centroid? Using that concept, we are writing here the centroid of this triangle PQR, and we know that summation T1 is 0, so this will not be there, and this is further simplified, and you have this. So the x coordinate being this, then we conclude that it is at a distance 2 by 3 h minus 2a from the vertex. That is the x distance, so that is considered here. We are asked to prove that the normals at the points where the straight line meets y square is equal to 4ax intersect on the normal at this. So the same problem can also be asked like this. So because there you can either follow this or this. We will now discuss this one. The equation of the chord PQ of the parabola of Lx plus My is equal to 1. Show that the normals at P and Q meet on the normal. So we are having 2 points P and Q. Equation of the chord PQ is given by, this is given by Lx plus My. Lx plus My equal to 1, and we have to show that the normals at P and Q intersect. So you consider the normal at this, you consider the normal at this, it has to meet at this point. So this is the aim. So if P and Q be the points T1 and T2, the normals at P and Q meet at R. So this R only we need to find. If T3 is the foot of the normal of the third one, so we shall time being we shall assume what that point as T3. We will take it as T3. Actually we need to find the coordinates. It is actually 83 square to 83 generally speaking, but here in terms of what he has given, we have to arrive at this 83 square to 83 is nothing but 4am square by h square, 4am by l. So let P and Q, and this result is known to us. The equation of the chord Lx plus My is equal to 1, and since P and Q lie on that, P is the point we have taken as T1, and this is taken as T2. So both of them satisfy the T1 stands for 81 square to 81. T1 squares, T1 stands for 81 square to 81, and the same way the other one, 82 square to 82. So in the place of x you have to replace it by 81 square, in the place of y you have to have 281. So that is what is done here, and from these two um, uh, we simplify and get our T3. From where T3 is obtained, we know that T1 plus T2 plus T3 is 0. So replacing T1 plus T2 by minus T3, we will get the value of T3 as this, and any point is again assumed as T3, 83 square to 83, just substitute what is needed, we will get. So this point up to this, it can be asked, because all this are based on, here you don't have any mathematical, geometric concept involved in this. All are just calculation, distance calculation, simplification from known relation, how further we can simplify and arrive at this. So that kind of thing is discussed here, so we will not concentrate on that. Simplification part you can see here. Show that from any point P 80 square to 80, that point is taken as this, two normals can be drawn. So we shall take that from any point HK, three normals can be drawn. So that point we shall take as, and the HK will take as 80 square to 80. So let the two roots to be T2 and T1 and T2, right? So actually we have given the normal, we have three roots. So two of them are taken as T1 and T2. If the normal at T1 and T2 meet the curve again at the point on y square is equal to 4x, so that is given to us. And this result we have already derived. Whenever we have normals at 2 points intersect on the parabola again, then product T1, T2, that's a very basic result, and quite often that will be used, and that's an important question also, that whenever we have the normals at T1 and T2 again intersect on the parabola, T1, T2 is equal to 2. So that result that we are going to use here, and this is known to us already. So T1 plus T2, the third one is taken as T, third one is taken as T. So you have T plus T1 plus T2 is equal to 0, and therefore T1 plus T2 is equal to minus T. T1 plus T2 is equal to minus T is known, and T1 T2 is equal to 2 is known. So why that is taken? Because of this condition only, T3 is taken as 80 square to 80. T3 is taken as just T. So sum of the roots known, product of the roots known, so the equation should be of this. So that is what we are having here. And this part, P is known, Q is known, R is known, use distance formula, and you have to get the answer in terms of only T. So here you have the process of eliminating your T1 and T2. How it is eliminated using T1 plus T2 is equal to minus T and T1 T2 is equal to 2 are explained here. Patiently you can go through later. And this type of problem in section B, you can expect, find the feet and the equation of three normals, two. So two things that we need to find. One is the feet of the normals. So if they ask for just feet of the normals, yes, it can be asked in section A, and together means you can expect it in section B. So you are given the equation of the parabola to be y square is equal to 8x. It is not 4x, it is 8x. So that gives naturally a as, because when you compare that with the standard form, it implies that a is 2. Y square is equal to 4x to be compared with y square is equal to 8x. So you get a is equal to 2. Now any point on the parabola 80 square to 80, a is 2 here, so you have 2t square 4t. So equation of the normal at this point, when we want to write, we know that y plus xt is equal to 280 plus 80 cube. So you replace your um, you have that equation, you replace your a by 2, so you arrive at this. Now we are given that this passes through the point 18 comma 12. So substitute that, you will get a cubic equation in t. Solving for the t, you get three values because it's a cubic equation, and the three values -1, -2, 3 that you have. So they give, when I consider the feet of the normals as T1, T2, T3, we have obtained what are they. So the first part of the question is answered here. The first part of the question is answered here. You are replacing your A by 2, and because it passes through. If this point is not given, then we cannot solve this. So if that is given, then we are able to solve it. And at the point this equation 1 becomes equation, it has to satisfy the equation 1, means this is equation 1. So t is equal to -1. When you substitute, you get t is eliminated, only y and x will be there. So you have that representing the equation of the normal at this point. And similarly for the other 2 points, we can easily find out the equation of the normal. And next is, if the normals at the points q r meet the parabola at p, and the tangents at q and r intersect at t, then show that the locus of the circumcenter of the triangle TRQ, it is actually TRQ, TRQ, triangle TRQ is the parabola something. So here again the technique that is to be discussed, we are asked to find the circumcenter. Now suppose I am given any triangle, by the circumcenter of this triangle we mean the bisectors, side bisectors, meeting point of the side bisectors. You have this side, the bisector of this is supposed to be midpoint, and in the same way for this side you have midpoint. And you consider the perpendicular bisector of the sides. Let them meet at the point M. That is called your circumcenter. So job is to show that the locus of the circumcenter is something. So which means I need, if I assume x1, y1, I have to arrive. Otherwise, what is that x1, y1? By solving. What is to be solved? See this, if I consider, if I am able to get the equation of nm and lm, solving those two equations, this point can be obtained. Or in the same way you can consider km, lm, any two you can consider, solve it, you will get the coordinates of m. So how to obtain this? So for which, if I know this is perpendicular, so this is perpendicular to this line. So if only I know the equation of this line, slope of which I can find, so that is one method. Or difference between y coordinates divided by difference between x coordinates will give me the slope. If the slope of this line is known, then we can easily obtain the slope of the perpendicular lm. So this point, if I'm this is known because this is the midpoint of these two. So this point is known, the slope of lm is known, so I can easily write out the equation of lm. This point is known because this is the midpoint of R and T. R is known, T is known, midpoint we can easily find. So one point, and the slope is known because this line is perpendicular to this line whose equation is known, right? In fact, we don't want the equation, slope is enough. Perpendiculars, the product of the slopes of the perpendicular is -1. So using that, if I know only the slope and I know the point, I can get the equation of ln. And the same way, get the equation of nm. Solve for your x1, I mean solve for them, x and y. You will have them as x1, y1. Then locus of that will give the this. So outline is this, but we will have to work out a lot. So let the normals at q and r on this meet the parabola at p of t3. So this we have taken. Then T1 plus T2 plus T3 is 0, and because the normals at T1 T2 meet the curve again. So this as said earlier is an important result. T1 T2 is equal to 2. Now let T be the point of intersection of the tangents at Q and R. Tangent. See, in this case both normals and tangents play a role. So we should not get confused. So here I consider the tangent, here I consider the tangent at Q and R. Let them meet at the point T. And the coordinates are known to us already, a T1 T2, a T1 plus T2. So here T1 T2 is 2, so you get this as 2a, and T1 plus T2 plus T3 is 0, so your T1 plus T2 is minus T3. So let M be the circumcenter of the triangle. Midpoint N is the midpoint of TQ, so that can be easily written. And slope, as I said earlier, difference between y coordinates divided by difference between x coordinates, that gives the slope of TQ. So you have the this one, slope of TQ is known. So first we obtain the equation of this, and the same way similarly we can put and we can have the equation of this. So first we obtain the equation of NM, right? So slope is known, perpendicular slope known, N known. Write out what is NM. So equation of NM is written, and similarly equation of LM. Let M be M of x1 y1, then M lies on both 3 and 4. It is the point of intersection. So perpendicular bisectors, intersecting point is the circumcenter, and substituting that, this is what we have, and all these calculations are to be done, and we are eliminating T3. So the process is to be understood line by line. Okay, here we are not going to explain them in detail. You can see it from the uploaded material. So we can that point, otherwise you yourself can derive and check the result. So locus we need to find, and dropping the suffix you get the locus. So here circumcenter definition should be known, and what is the midpoint and what is the point of intersection, and how do we obtain the equation NM, and similarly obtain LM, solve and then eliminate T3. So step by step you write out what are the points in this to arrive at the solution. So then that can be easily understood. And this orthocenter problem already we have discussed, and it is actually continuation of the previous one that you can easily understand. So we don't spend time on this 10th one. And in the parabola, find the points of contact of tangents from 2, 3 and prove that the corresponding normals intersect on the parabola. So normals, first we find out the feet of the normal, 2 feet, and you write out the equation of the normal at that point and another point, solve for it, and you must be able to show that this is again a point on the given parabola. So replace x by 9, so 36, replace y by minus 6, that is also 36. So in that way we can conclude that this is a point on this. But how this point is obtained? By solving these two. And then how do we arrive at these two equations? So for which the tangents from t of 2 comma 3 to y square is equal to 4x meet the parabola at p of t1 and q of t2. So t is, this is the problem, and the see the tangents from, see it's something like this, that you have tangents from 2 comma 3. So you have something like this. You have somewhere say 2, 3 somewhere here. From that 2 tangents are drawn, right? They meet the curve at the point T1. It has to touch actually at T2. So this point, otherwise you know as AT1, T2, AT1 plus T2. But what he has given them the coordinates as 2, 3. So only you are equating this one to 2 and this one to 3. And from that you are getting T1, T2, sum of the roots, product of the roots known. So individual values you can easily find out. Otherwise, in a roundabout method also you can do, that's time consuming. So this is, even this kind of technique you would have used in theory of equations to get the roots, individual roots. So, and these problems, as I said earlier, from this problem onwards, uh, the point of intersection of the normals, 2a plus at1 square plus t1 t2, this has to be remembered. Minus, we had the coordinates of the point of intersection of the tangents to be this. This is point of intersection of tangents, and this is point of intersection of the normals at t1 and t2. So both are to be remembered. Um, so here, and just again, you'll have to make use of distance formula, and you will arrive at this. And so again, in all these, you will be using this one is different for the reason that it passes through the focal cord. You are using the n to be the point of intersection of the normals. Point of intersection of the normals you take as n, right? And the card passes through the point a comma 0. So that is given to us. So consider a focal card PQ of y square is equal to 4x. The problem is this: find the locus of the point of intersection of the normals at the ends of a focal card. I have a parabola, I have a focal card, the one which passes through this. So what we have to show is the normals are these two at the ends of the focal card. We have to find out the locus of this, right? You have PQ to be the focal card. So we know that the card joining P of T1 and Q of T2 is given by P of T1 and Q of T2 is given by y of y into T1 plus T2 equal to 2 into x plus at1 T2, and this passes, because it's a focal card, it passes through A0, so you have T1 T2 is equal to -1. So this is some this kind of relation between T1 and T2. Once it is obtained, that can be used in this place, and further simplification can be done. So that is the technique that they are using here. So to arrive at the relation between T1 and T2, in each and every problem, conditions will differ. That is it. So, but the technique is the same. You need to remember this, and how to get rid of this T1, T2. So that once that is not present in the final step, you can easily obtain the locus by just swapping the suffix. So that is the idea. So that in order to arrive at that, in each and every problem, the condition given will differ. That is all. So T1, T2. So here you are getting T1, T2 is equal to -1, and in the other problem you will get not the same thing that you will have. Here condition will differ, but anyhow you will get T1, T2 is equal to the relation between the two you will get, and here again T1, T2 is equal to 1. So here the condition is different, but in all the cases the point of intersection of the normals, whether you consider 15th problem or the previous one or this one, so in all you have the coordinates of the point of intersection of the normals, that is this, and how we obtain T1, T2 is equal to something. So depends here focal card, so -1, and then the next one some other condition is given that we will see. So in that condition, again in that situation, what is the relation between T1 and T2, that is obtained here. But again the same point of intersection of the normals is considered, and here some other condition is given, your T1, T2 is equal to 1. So these problems are based on that, and nothing special to explain in this. You have to have how to get the relation between T1 and T2. So that is the main part. Otherwise, the procedure will get repeated in all the problems. Then in the same thing, there is a one more show that the midpoint of PQ lies on. So midpoint is taken when you are asked to show that the midpoint lies on is same as finding the locus of midpoint. So the meaning is the same but worded differently. So you'll have to find the locus of x2, y2, and midpoint means x1, y1, x2, y2 means x1 plus x2 by 2, y1 plus y2 by 2. So that is used. These are simple things. And here tangents are drawn to a parabola from any point on the directrix. So here is the trick to arrive at T1, T2 is equal to -1. Show that the normals at the points of contact are perpendicular to each other and that they intersect on another parabola. So they are perpendicular to each other. Once you arrive at T1, T2 is equal to -1, that one will come. So let T of minus a comma y2 be any point on the directrix x plus a is equal to 0. Let the tangents from T meet y square is equal to 4ax at P of T1 and Q of T2. Then T is the point of intersection of the tangents at P and Q. So the same thing that 2 comma 3 there we had something similar to that you have here, and this is that point T. The point is also interpreted as this, right? So you have from here, this is the point on the directrix x plus a is equal to 0. So naturally any point on that will be minus a comma y2. Why y1 is not used, locus later we need, so that is reason. Nothing wrong, y1 you can use later, you can use y2, that doesn't matter. So this is visualized in two ways. One is point intersection of the tangents at T1 and T2. So you have a T1, T2, a T1 plus T2, but that point is also minus a comma y2. So equating the x coordinate, T1, T2 is equal to -1. Now the slope of normal at T1 is minus T1. Slope of the normal at T2 is minus T2. From this equation you can easily see. So product of the slope must be -1 for them to be perpendicular, and that is what we have from here. So they are perpendicular to each other. And for the second part, as said earlier, the coordinates of the point intersection are to be known. Only then we will arrive at that. And so here again, point of intersection of the normals only we need, and the relation T1, T2 is equal to 1, how it is obtained. So for that some condition is given. Two normals to this make complementary angles over the x-axis, prove that the locus of the point of intersection is a parabola. Point of intersection, that point is known. Now T1, T2 is equal to T1, T2 is equal to 1 in this case. How to arrive at that? So we shall take the normals intersecting at the point x2, y2. Right, you have this. Slope of the normal at P of T1 is minus T1, at Q of T2 minus T2, known already, and theta1, theta2 be the angles made by the normals with the x-axis. So once that is known, M1 is taken as tan theta 1 and M2 is taken as tan theta 2. So that is minus T1 minus T2. What is given to us is they make complementary angles. So theta 1 plus theta 2 should be 90 degrees. That's given. So tan of this is infinity, which means tan A plus tan B formula. Tan A plus tan B divided by 1 minus tan A tan B is infinity, which means whatever I have in the denominator should be 0, and that gives T1, T2 is equal to 1. Point of intersection is taken as x2, in that replace T1. That how to simplify that, and that's purely a simple calculation, algebraic, no this thing is geometry is used there, just algebra is used, and the steps given in the last problem are self-explanatory. When two of the three normals that can be drawn from a point is coincide, then P lies on the curve. So you have here again your two, see, T1, T2, usually T1, T2, T3 are taken as the feet of the normals. What he has given is T1 coincides with T2. So your T1 equals T2. So when we use that fact here, T1 plus T2 plus T3 now will now become. You don't have, okay, we can even take this instead of T3, we shall take, say, our T1, T2 present, right? T1, T2 present, and the other one T2 equals T1 equals T3, like that also you can take, so that you will have T1 plus T1 plus T1 T2. So in the same way here also T3 should be replaced by T1. So you will arrive at all this. So from here T2 is known, and it is just the simplification from what is known, the relation. So all these problems, unless you have practice, cannot be recalled, cannot be worked out on your own. You need first to know about the technique involved, and then you have to work it out. Only then it could be easily uh, again recalled, and you can write it again. So this is all in section 32 with 17 problems. So